Good evening, and thank you very much, Google, for providing the site and the invitation. This is one of a series of talks about the MIL general purpose CPU architecture. This one is about the internal data structures and how data is communicated within the machine from operation to operation, and the programmer's model that works on that the programmer sees. We'll touch a little bit about how it's implemented on the inside as well. To do this, I need to touch lightly on the available choices for architectures which are out there. These are a couple of top of the line, or at least they were top of the line when I went to go get the numbers, top of the line CPUs from major manufacturers. This one has got 4 cores on a chip, each putting out 4 operations per cycle peak, 3.3 gigahertz, burning 130 watts, giving you 52 gigabit operations per second and costing $885, quantity 1,000. Architecturally, this is a out-of-order superscalar architecture. You can probably guess which one, but what constitutes top of the line changes week by week, so look a couple of months back. A different one has got a single core, which can issue 8 operations peak per cycle, half a gigahertz, only 1.1 watts, and only 3.6 giga instructions per second. But you can buy them quantity of 1,000 for 17 bucks. This is an in-order VLIW used for DSP work. Now, to compare these two, the out-of-order is giving you 406 MIPS per watt and 59 MIPS per dollar purchase cost, whereas the in-order is doing a little different. If you compare these two on a per core basis, because if you recall, the out-of-order had 4 cores, the superscalar gives you a little bit better than 3.5 times better performance per core, but it costs 30 times as much power and 13 times as much money. Now, there's a rather striking disparity here, and how is it that such a difference in power and price is maintainable in the marketplace? You'd think that somebody would have arbitraged it away. Well, one of the major reasons is that the DSP is only a 32-bit machine, whereas the superscalar is a 64-bit machine. In addition, if you need raw horsepower, you're not going to get it out of the DSP. You need the superscalar. But the major reason is that the workloads are fundamentally incompatible. Signal processing is just not the same as general purpose code. A DSP VLIW working to run the laptop in front of me would be truly horrible. Now, it's true that if you have a DSP workload, you could probably run that superscalar against it so long as you had enough Freon to keep it cool. So our goal as a chip design company and the technical challenge, we wanted to get DSP efficiency, but do so on general purpose workloads. We've been at it for nearly 10 years. This is a sample of the result. This chip has got 2 cores, issuing each 33 operations per cycle. Only 1,200 megahertz, a third of what the superscalar does, but only 28 watts too, giving you not quite 80 giga operations per cycle, peak, and $225. Now, this is vaporware. We are several years still away from having something with pins on the bottom. So the clock and power is our best estimate as professional design engineers based on several years of sim. And the price is anybody's guess, but we don't even own a marketing department. And the longer that lasts, the happier I'll be. That's the mill gold chip, or 2 gold cores in 1 chip. That's what you get for overall. To make that same per core comparison, compared to the VLIW, it's got 11 times more performance at 12 times more power. So we were successful. We had a linear scaling compared to the VLIW. Take the price the difference with a grain of salt. Compared to the out of order, per core, not quite 2.5 times the performance, not quite 2.5 times less power, and not quite 2 times less money. Now, you may have noticed that line there, issuing 33 operations per cycle. No chip out there issues 33 operations per cycle. And a large part of what we had to do in order to get that goal was to figure out a way to have 33 operations per cycle. Now, these are 33 independent MIMD instructions. We are not talking SIMD. We're not talking vector operations where every operation in the vector counts as a separate one. If you count it like that, that goal is doing 500 operations per cycle peak. But these are MIMD, completely independent, branches, adds, what have you. Moreover, the operations must match the functional unit population which is present on the chip. That's not 33 adds. It's 33 mix-stops, which on the gold can include up to 8 adds. So, 33 ops. Why? Well, the great majority of operations in code are in loops. The DSP code, all those loops are software pipelined, and software pipelines have unbounded ILP. This is instruction level parallelism. This is the potential parallelism. It's not the realized parallelism, which is IPC, instructions per cycle, which depends on how many adders you have. No matter what your potential parallelism, you cannot do more adds than you have adders. So it has unbounded ILP, and if we throw more adders at it, well, we can make use of that ILP. The DSP loops are software pipelined, but rather few general purpose loops can be software pipelined. They contain really nasty things like function calls and embedded flow of control and assorted other things, which makes it very difficult for them to be software pipelined. If you're doing linear algebra, you can software pipeline just do it fairly well. And in fact, the codes will do that, and things like those VLIWs do quite well in linear algebra. But the kind of things like this PowerPoint in the program here, which is your typical general purpose code, does not pipeline very well, at least on conventional architectures. So our solution was, of course, not to be a conventional architecture and add facilities which permit us to pipeline across nearly all loops, including the ones I described with embedded calls and things like that, and to throw function hardware at it. An adder is a tiny, tiny little thing. On a modern machine, essentially all of the functional units, the adders, the multipliers, the vector units, the shuffles, all of those all together will be 8 or 9% of the chip area and a power budget. Nearly all of what that superscaler is doing is figuring out what it's going to do next, get ready to do it, actually do it, and then figure it out how to get what it just did to the guy who has to do it next. That's where all the budget goes. And we can add vast quantities of more functional units cheaply in terms of area and power. Anybody can, we can too. The result, loops less than 15% of cycles. Now, I'm not going to say we've repealed Amdahl's law. It's a whole other story having to do with things which are not in loops, which obviously once loops have been beaten down, the things which are not in loops become the problem, but that's not this talk. We'll address that a different day. How to do it? The biggest problem is decode. That's a different talk too. In fact, that's a talk that was already given in May. I'm not sure if any of you, yes, some of you were there at Stanford in their EE 380 seminar, and talked about how we are able to decode 33 operations per cycle, variable length operations, x86 type variable length. And how to do that is an interesting story, but it's not this story. However, there are videos and slides and what have you, and that's where you go if you want to see how we did it. This includes a video of that presentation and the slides from it. So, besides the decode problem, the other problem is data. How do you feed data from operation to operation for 30 plus operations per cycle? It ain't easy. Every cycle. Now what follows is a gross oversimplification. Most of you do not have ever seen the inside of the guts of a CPU at the designer level. They are incredibly complex beasts. And what I'm trying to do is convey an intuitive understanding of the nature of the problem. Any of you who actually do chip design know I'm lying through my teeth, but at least you'll get a sense of the order of magnitude of the problem and where some of the issues lie. CPUs are extraordinarily complicated, and designs vary wildly between and across lines. So, gross simplification. The basic problem is that there are a lot of data sources. The Haswell is an example. Every one of these things can be the source of an ad or something like that. Nearly 500 possible sources. There are a lot of sinks, people who will consume this data. Again, Haswell, nearly 100 sinks. Well, all those sources and all those sinks need hardware to connect them, with the data flowing, full width data flowing along each connection so that any source can feed any sink. It's 50,000 connections possible. The fundamental tool used to do the hookup, well, meet the multiplexer. A tiny circuit. It has two inputs at the top, data input, and a control input to the right, and one output. And the control input selects either the left-hand input or the right-hand input to route to the output. Now, if we go back to our sources and sinks, and take our multiplexer, we can hook that to one of those sinks. And then we can hook a whole pile of them. And then we can route our data by setting the control lines to the set of multiplexers so that it falls correctly down the tree of multiplexers to get to the right output. There are many other implementations besides the tree multiplexers. I'm simplifying. However, the important thing here is that the latency, the length of time it takes to get something from a source to a sink, is proportional to the depth of that connection path, which is, of course, log of the number of sources, because each source has to get to each sink. The power is proportional to the product of the sources and sinks. Again, simplifying, but log of 500 is 9 levels, which will be at least 3 pipe stages, increasing your pipeline length. And when it all comes down to it, this interconnect tends to, on a superscalar such as the Haswell, will tend to consume around half of the overall power of the chip, of the core. There are solutions, there are alternatives. These and many more have been tried. These and many more actually exist in the chips you use. They all help, but nothing really solves the problem, which is why the superscaler had 30x the power cost of the VLIW. The VLIW doesn't have 500 sources. It had 8 sources. So the performance limit is the power time ceiling for data distribution. Why have all those sources? There's only 32 program registers. All those extra registers are rename registers. Why do rename? Say this is your initial source code, which would be, in a naive compiler, would produce this as your machine instructions. Get a temporary register, we add the A and B registers and put the result in the temp, increment the temp by 1 and put the result in our result register, and similarly for the second expression. Now you'd think that because the two expressions there, the two assignments in the source are totally independent, that they could be run in parallel. And in fact, they can be run in parallel because there's no data dependency between them. You could run the add and subtract of each one in the first cycle, and then the increment in the second add in the second cycle, and all would be well. Except for one slight problem. You notice that above the dotted line, which is the cycle boundary, that we are assigning twice to RT. Oops. When RT is referenced in the second line, which value does it get? Or perhaps some bit merge of the two values. This is called a hazard, and rename is a device used to avoid hazard in processors. Instead of doing that, the hardware renames the two uses of RT to RT1 and RT2, making use of this vast pool of rename registers it has at hand, and turns the code so it looks as if the compiler had said that instead. Those don't collide. No hazard there. The RT1 assignment does not collide with the RT2 assignment. The RT1 and the RT2 use will get an honest value. Away we go. That's why rename is used. Now, why does the compiler reuse the registers like in that example? Well, it runs out of registers. 32 aren't enough. Or, on some machines, even if it doesn't use rename, it still has a ton of registers. There's no easy way to mark the last use, so it's hard for the hardware to know that it's safe to reuse a register. There's been a ton of marketing proposals, but none of them quite work. And the registers are also used for call arguments, and you don't really know whether the called function is going to use them or not all too often. What are all these steps used for? 80% are referenced exactly once. They are used solely to indicate the data flow connection from one operation or another. The result of this add is going to be used by that multiply and will never be used for anything else. 14% are referenced 2 or more times. And in this case, the registers are simply being used as fast memory. Convenient place to stash a value you're going to reference a few times in the near future. 6% are never referenced. This result coming from Yale Pat and one of his students. So, split those two uses. Have one mechanism for the local memory kind of use and one mechanism for the data flow connection. Are there any machines that don't use registers to indicate the data flow? Well, yes. An accumulator machine. Those of you who are ancient enough to remember what an accumulator machine is, well, all operations implicitly address the accumulator. So the result and one source operand are implicitly addressed, and the kind of hazards described are impossible. A stack machine. Result in both addresses are implicitly addressed. Now take that stack example. The adder can take two values off the top of the stack, add them, and push the result back on top of the stack. No possible hazard there. No need for rename whatsoever. But you only have one top of stack, so you can only do one operation at a time. And our goal, of course, was to do two operations at a time, which we couldn't do. Only one at a time. What you really want is several stacks. But they need to be interleaved. And you want them to be, any operand within them to be usable by the functional units in parallel. Well, that's the way the mill works. We call it the belt. It works like a conveyor belt. This is a programmer's model. It's a conceptual model. There's actually no huge shift register in the inside, and I'll get to how it works actually on the inside later. But it's a fixed length FIFO. Functional units can read any position. Pop in goes the add. Results drop on the front, pushing the belt along with the last values falling off the back. This is your programmer's model. This is what you're programming into. There are no general registers. Your adds take values off the belt, drop the result in the belt. The next operation can pick them up off the belt. Functional units can read any mix of the positions. You can have as many functional units as you want. All results in any given cycle drop together at the start of the belt, pushing as an equivalent number off the back end. The belt addressing, belt things, instead of being register 3 and register 5, which is fixed forever like the pigeonhole in a post office, instead belts are addressed by relative position. This is a mill assembly language statement. Note that there is no result address specified. You don't say where the result is going to go. That makes your code more compact, which is rather important for things like your instruction cache. So B3 there is it indexes from 0, is the fourth most recent value to have dropped onto the belt. B5 is the sixth most recent value that has dropped onto the belt. This is temporal addressing. It is not spatial addressing, it's temporal addressing. Now, take that brick-colored value 8, which is presently at belt position B3. That position and its name, its address, will change every time a new value drops onto the belt. So, if 3 values drop onto the belt, B3 now refers to a different value, and our former value is now B6 in this cycle. Writing hand code for this is not a pleasant exercise. It is trivial for a compiler code generator, however. Now, the things I show you falling off the back end, they are definitely use it or lose it. But in order to reduce the possibility that something you really want falls off the back end, your best code will come if the compiler schedules producers very close to consumers, because that means that the produced value is likely to still be on the belt when the consumer wants it. In practice, the belt size is set such that nearly all one-use values are consumed immediately while they're first in the belt. But the guys which do have to be kept for later or referenced more than once, we don't have to rename them, we don't have to put them anywhere while they're on the belt, but we do need to put them somewhere for after they fall off. And what was 300 rename registers in a superscaler is belt lengths of 8, 16, or 32, depending on the family member. The mill is an architectural family in the sense that the 360 was a family ranging from relatively small to super bazoo with different belt lengths, but those are your typical belt lengths. Long live values must be saved. The way you do that is with a scratchpad. The scratchpad is a hardware, actually SRAM structure. It is not part of memory. It is not addressable as memory. You can't index into it. You can't have pointers into it. It is a device for holding values that you're going to want to use later. So, for example, the spill operation will take a value off of the belt and put it at a location in the scratchpad. Later on, when you want it back again, the fill operation will, naturally enough, drop it at the front of the belt and push something off the back. The scratchpad is frame local. Each new function gets its own full scratchpad. Or at least that's the illusion we provide. It has a fixed maximum size defined by the family member, and the function must explicitly allocate and say how many scratchpad locations it wants to be able to use, which is what permits us to have an efficient way of providing the illusion of infinite scratchpad. The addressing is static by byte. As I say, no pointers, no computer addresses, purely static. Put it here, I want it back again. It's a 3-cycle spill to fill latency. This means that if you want a value to use again, and you want to use a scratchpad, well, you spill now and you won't actually get the thing back for another 3 cycles, which means that in turn that we set the length of the belt so that nearly everything lives for 3 cycles on the belt. Now, the belt naturally lends itself to operations with multiple results. There's a canonical pain in the neck in instruction set design called divide. Divide wants to produce a quotient and a remainder, whereas all the rest of the machine is all designed for 2 in and 1 out, adds, multiplies, and what have you. And if you look at the instruction set of any machine of your choice, you will discover a horrible kludge called divide. Sometimes there's special registers, sometimes there are register pairs, sometimes there's this, sometimes there's that, but it's always a kludge. There's our divide functional unit, 2 in and 2 out. Well, the 2 in is no problem. It grabs 2 items off the belt just like anybody else. And of course, divide chugs for a little while. The horizontal dotted lines are cycle boundaries. And it chugs a little longer, and finally it's about ready to produce a result, which it can drop 2 results. No problem. Function calls. Assume that this is your caller's belt. And this is the call operation. Func is whoever we're calling, and the other 4 things there are belt positions for function arguments. No, you do not have to load the registers. No, you don't have to save registers. No, there's no warm-up protocol to get your stack. Call operation. That's all there is. So, 1 cycle later, we are now in the callee, and he has an empty belt, brand new scratch. Except that it has been preloaded with copies of the actual arguments. He operates for a while. Double dotted lines mean some unknown number of cycles. And let's say at the end, when he's all done, he gets this belt. And he executes a return operation. 1 cycle later, the original caller's belt is now available, untouched, unchanged, where the new result is dropped.
Can you return more than one value?
You got it. So a call has the same effects as an operation like add, and a call can drop multiple results. All of the things like, for example, output arguments in Ada and standard colon pair and a colon pair and all of those other things which are kludges to get around to the fact that programming languages are devised to mimic human languages with left to right visible things and the inability to produce a true data flow graph in a conventional programming language. They all get turned by your tool chain into functions with multiple results. Now, I said that the former belt magically reappears after the call. That magic is called the spiller. It is a background engine that does the save and the restore. We didn't invent this concept. Those of you who are familiar with the Spark architecture and register Windows or similar engines in the Itanium or whatever, the important thing is that you don't have to program it. It will take care of it before you, behind your back. And the later slides will touch a little bit on how it does it, but that's the spiller. The values in the belt are marked with the originating frame. In addition to saying you're number 3, you're also frame ID 742 or whatever. So your belt access that a running program has is only to the values which are tagged with the current frame. So consequently, if you change the current frame ID, your belt's empty. Bing, just like that. Because you no longer have any values you can address with your frame ID in them. But the data is still there in the buffers and the registers and what have you, and can be spilled at leisure by the spiller. Arguments are passed by copy, and of course they get the new frame ID, the callee's frame ID, so the callee can reference them. Note that the caller cannot reference them. Wrong frame ID. Now, functional units get collected into pipelines. There may be an ALU and a shifter and a few other things all in one group which shares a common data input. And these are sometimes referred to as slots or pipelines or clusters. Each pipeline on the mill and on most machines has exactly 2 data inputs that are shared by all the functional units within the pipeline. Those functional units also share several outputs, but the outputs are organized by operation latency, so that there's an output for each operation latency. And a simple add that's a one-cycle operation will go out the latency 1 output, whereas a multiply, latency 3, has got a different set of outputs. Those, in turn, feed into output registers, which simply data capture the result of the functional unit. The adder just falls into this register. That's an internal register, it's not an addressable register. There is, however, an output register for each latency, for each result, because like divide, things can produce more than one result that the pipeline can produce. So consequently, because every one of those output registers could be an input for some other consumer, all those output registers are sources. There are a few special cases that add additional sources. And for various reasons having to do with encoding, we have to have at least twice the belt length total. Now, it happens that the sources on a gold do not add up to twice the belt length, so we have to add extra buffers so as to provide a total of 64 sources versus 450. This is the major reason why we are showing DSP power rather than superscalar power consumption. The mill is a wide issue machine like a VLIW or a Itanium. A single instruction contains several operations. All of those operations issue simultaneously and are executed together. The positions, the textual position within the instruction are referred to as slots. This is a common terminology in the VLIW world. And the instruction slots in numeric order correspond to function pipelines in order. So when the decode routes the ops to the corresponding pipelines, it's an exposed pipeline machine. What that means is that the latency of operations is visible to the program. When you do an add, the result of the add will be available to an operation in the next cycle. You do a multiply, the result of the multiply will not be available to an operation in the next cycle, in the next instruction. It will be available 3 cycles later or however long the latency is. And this is exposed. This is a very common machine organization for DSPs and VLIWs in general. It is not used at all in things like superscalars, whose whole point is to hide latency. So let's say that this is our original code, A plus B minus C times D. Well, obviously, our first instruction is going to have the add and the multiply, because they can be done in parallel. We can't do the subtract until later. And those will go to 2 functional units, an adder and a multiplier. And a cycle later, we're going to need to be able to make use of the results of these guys, so we're going to have an instruction which is the subtract instruction, and it's going to need a subtract functional unit. And there's the result of our add, and it's ready now, but the multiply is not yet ready. So what we need is to recognize the fact that it's not ready, and we want them both to be ready. So if we wait for another cycle, now they both are, they go into the subtract, and our final expression comes out the bottom. Now the question, of course, is where does that thing, the A plus B, where does it sit in the meantime? Well, it could sit on the belt, but that clutters up the belt. You really don't want to have things be sitting around on the belt. So the belt usage is best when the producers feed directly to the consumers. So this will give you better belt consumption code. The multiply starts, the add starts a cycle later, the subtract starts a cycle after that, and away we go. Now, note that, because we only had one multiply happening in that first cycle now, the slot, that is the pipeline that did have the add in, it is now free, and you can put a different operation in there to do something for somebody else. So all of these things can be made use of each cycle, but the way to lay them out is best if the consumers go directly to the producers go directly to the consumers. Which raises a question of what do you do with the multiplies if you have a call while the multiply is still happening? Well, let's say that's our belt, and we do a signed integer multiply. That's what a MOLS operation is. There's our multiply unit. A cycle later, let's assume that nobody retired, so we still have the same belt that we did before. And we do a call. A cycle after that, we're now in the callee, and the multiply has done its thing, and it's ready to retire. We're still in the callee. Should we drop the new multiply result, which was started back in the caller, into the middle of the callee? Nah. So let's rewind things. We're back in the call. We go in the callee and we let the entire callee run. in full. Eventually he comes back, and let's say this is his belt this is our original belt with the 2, which is the result of the calling. Now the multiply retires. So the multiply retires in the frame in which it was issued. Intervening calls are like intervening adds. Nothing happened.
So
Calls
where was
are-
that result in the meantime? Where was that result in the meantime? You can't be in the multiplier or you'd be screwed.
Coming up. Fundamentally, the answer is a spiller, but coming up. So calls are atomic, and inflates retire after the call returns, which is a good thing because there's something called an interrupt, which can be happening in the middle of one of your multiplies, and is on a mill nothing but a spontaneous function call that you didn't have to code. It is implemented exactly the same way. They're just involuntary calls. The hardware vectors to the entry point. The hardware supplies arguments in the interrupt vector handler's belt. The handler arrives, and there's all its arguments supplied by the hardware. There's no doubled state. We don't have to have a whole set of registers for the interrupts and another whole set of registers for the application. There's no task switch. We don't have to flush the pipeline, just like a call. And there's no restart penalty after the return. The only penalty you're going to pay on an interrupt is because the decoder wasn't expecting the interrupt. And it has busily been decoding code around your application, and suddenly it got an interrupt, so it had to mispredict. And a mispredict on the mill is 4 cycles plus the top level cache time total. And that's the only delay. Data forwarding. I said before, this is not a whopping big shift register. Whopping big shift registers are rather expensive. Instead, internally, the way the data gets forwarded is through a 2-stage crossbar. There's a lot of ways of implementing this crossbar, including those mux trees that I described, and people who are of the software persuasion, such as myself, tend to leave those choices up to the hardware guys with the bolts and let them choose how they want to implement it. So I'm giving you the model of it, and the implementation may vary from chip to chip. It's a 2-stage crossbar because one set of results have to get to their consumer real fast. And those set of results are the guys who were produced by 1-cycle operations, adds, shifts, bit ops, that kind of stuff. And if we're going to do a back-to-back add to add to add to add to add as fast as possible, we need those to be able to happen once per cycle, straight through. So there is a custom crossbar from everybody who can produce a 1-cycle operation, which in practice is the ALUs, to all the consumers. That 1-cycle crossbar, to do that back-to-back, the cost in terms of what the signals have to go through is 1 or 2 latencies, depending on how many ALUs you have. The gold there with 8, and I think two additional latency ones besides the ALUs. It requires two levels of muxes, but it's relatively small. Everybody else has to go through a separate crossbar. The floating point units, the shuffle units, everything else goes through the latency n crossbar, which winnows all of those inputs down to 2 inputs, which in turn are routed into the latency 1 crossbar, which routes them to everything. Now the timing on that looks like this. That 32-bit add is a 1-cycle operation. In fact, this defines our cycle. We set our clock rate so that a 32-bit add plus the latency 1 crossbar is 1 cycle. So there are our clock barriers, our clock boundaries. Everybody else, the multiplies and what have you, they're running across several clock boundaries internally to do their thing. They can use a little bit of that trailing cycle because the latency n crossbar doesn't use the whole of the cycle, so they can make use of a little bit of it. Then they go through the latency, the results go through the latency n, through the latency 1, and out to the consumers. So that's the way the timing works internally. Now you can have multiple retires. Each pipeline can issue one operation per cycle, period. This is determined by the way the operations are encoded. There's one per slot in the encoding, and that means there's one per pipeline in the actually get issued. That operation will retire some latency cycles later. This illustration is describing just one pipeline, not all the pipelines. This is just one pipeline, and time is increasing downward as I'm showing you events as they happen one at a time. Now add B, that's a binary floating point add. It's a 4-cycle op. And that little brick-colored thing there is the partial internal state inside the floating point add unit. It's working its way down the floating point pipeline within that unit. It's not mucking with anybody else's unit, which is also in that pipeline. It's only in the floating point add unit. One cycle later, it is now still being worked on. It's still in the internal state. And we're now able to issue a signed integer multiply with 3-cycle operation. And the green there is now the internal state in the integer multiply unit. One cycle later, the widen M operation actually is a operation that is a vector operation that takes a vector of shorts and turns it into 2 vectors of word, or similar. So it has 2 results, and it is a 2-cycle operation. One cycle after that, our friend the unsigned integer add, 1 cycle, the yellow over there. Each one of these is in some state within the pipeline of its own functional unit. Because each of those functional units, I could have done 4 add Bs, and I would have internal state of one add that's gotten 1 cycle done, and one add that's gotten 2 cycles done, and one add that's gotten 3 cycles done. I'm showing them as different ops just so that we can see the different latencies happen. So, a cycle after that, we're ready to retire, and they all go off to the belt. Different latencies can retire simultaneously. Each functional pipe has an output register, described earlier. Assume that now what we're doing is we're going to do a sequence of integer adds. It's one after another, after another, after another. Well, 1 cycle later, it goes to the latency 1 output. We do another add. Problem is the latency 1 output is occupied. It's still in use. But the latency 2 is free. And furthermore, the latency 2 must be free. Because the only way that we could have something coming out of the latency 2 is if we started a latency 2 operation a cycle ago, and we didn't. We started an add. So if you work it through, you see that there cannot be a collision here. So that add will go. We can move the guy that used to be in the latency 1 to the latency 2 register and put our new latency 1 result into that latency register. Well, this obviously daisy chains nicely. The next add the effect of this is that when we need to save values in response to saving values, within any given pipeline, they can always daisy chain to the next higher latency each cycle. So the save that we have to do, we only have to save the values that are coming off the longest latency register. Everybody else can simply move along. Of course, now all the latency registers are full. Now what? Well, now there are separate data paths. We have to pull a value off that lat4. One possibility is there may be a vacant register in another pipeline. It's a different pipeline, and we can do that. Alternatively, the spiller maintains a bank of buffer registers. The save may go to that. In response to your question about what do we do with the multiply over the call, it eventually, through this chain, will wind up in the spiller buffer registers, and the spiller will move it down into the spiller save morass that it saves things into. First SRAM, and eventually, if it lasts long enough, eventually into DRAM, or into the memory hierarchy. Eventually, that will wind up being replayed by the spiller and made available at the top level registers. Now, if there are always more latency registers than there can be belt positions, and everything always has a place to go to, if necessary, add buffer registers. There are a ton of other possible implementations in hardware. You can use a register file. You can implement the belt as a CAM. There are others. I'm giving you the conceptual model here. How it gets implemented is transparent to software. And the choice is based entirely on power and clock and design tools, EDA tools. That's how you want to do it. So, keeping track of all this, the mill is in order, operations execute in program order. It's statically scheduled. The compiler controls when operations issue, not the hardware deciding when to do things out of order. The compiler says it. It has an exposed pipeline, so because the compiler knows when it issued it, the compiler also knows when it's going to retire. There are no general registers. Transient data lives on the belt. It does not do rename, because all the values on the belt are static single assignment. They cannot cause hazards, so rename is unnecessary. Correspondingly, there are no issue, schedule, or retire stages in the pipeline. If you go and look at an Antec or somebody else who will show you the Haswell pipeline, you'll see stages here, stages after stages after stages. Not as bad as the P4 NetBurst architecture, which had 30-odd stages, but still a lot of stages. The mill has only 4, which means that a mispredict is a third of the cost of a mispredict on a different machine. We don't have to encode the result address. It's always implicit. And consequently, the code is more compact. We save bits and power in the instruction cache. Actually handles multi-result operations. And calls and returns are one cycle and one op. It does not require either a prelude or a postlude. And you can have up to a belt full of arguments. If you have more than a belt full, or if you're passing whopping big structs, or you are passing varargs and other such things, those get passed to memory just like everybody does. But the overwhelming bulk of functions can pass their values in the belt. Anything you can pass in the registers, you can pass in the belt. You can get a whole lot more at tbcomp.com. 2 things there that you should look at, one of which is the docs that'll lead you off into other white papers, videos, what have you, more coming. But also there's a mailing list there that will send you to. This is a technical mailing list. We do not have marketing, so we don't have a marketing mailing list. But what it will contain, among other things, is the announcement of availability of new things like white papers and of further talks in this series. We know that we have talks coming up in IEEE, 2 more talks at Stanford, 1 talk believed to be at Microsoft, and so forth. They'll be each on different aspects of the machine. I think the next one we'll be doing will be on the memory hierarchy and how we are able to avoid stalls, which are the bane of statically scheduled machines. We're open to questions.
So question, it's not particularly clear to me how does this architecture play with scheduling between different threads or different processes. So what is involved at the level of, let's say, operating system to save the state?
Well, at the machine level, machines don't know about operating systems. So the short answer is that it's a general purpose machine. It's designed to run commodity operating systems, Linux, Windows, what have you. If you think about the way that the function call works, you can probably imagine the way a task switch works. That is, you call into something, and it returns back into somebody else. And the spiller handles that. Not covered today, this is a different talk, is our protection mechanism. The mill does not have rings, it has no supervisor mode, there are no privileged operations. All protection is done through the memory addressing environment. If you can address it, you can use it. Or more correctly, you can always address it, but if you can use the address, you can use it. This includes task switch, thread switch. We do not do multi-threading in the currently defined chips. The reason for this is a lot of SIM has told us that a given amount of hardware real estate and power is better devoted to more cores than to more threads in one core. The reason why multi-threading is used on the superscalers is because they have to be able to hide the cost of an L2 miss. And a simple way of doing this is just add yet more state in the core and then switch that state if you've got nothing else to do. The mill, for various reasons that I can't go into because the patents are not yet filed, but will be covered in future talks because we're filing patents as fast as we can. The reason why I can talk about this is the patents for this is in. The mill fundamentally doesn't miss that much, and we don't see memory stall as being as big a problem as it is on a conventional chip for our architecture. Now granted, we're still subject to memory stall. If what your program does is random references into a hash table that's bigger than all our cache, we'll run at memory speed, and so will everybody else. We have not, we're not doing magic here, but we are able to hide everything that a superscaler can hide using multi-threading, but without multi-threading. And consequently, the hardware resources are better put into multiple cores rather than multi-threads. You could do multi-thread. It just doesn't seem to be worthwhile.
I was a little bit confused on the relationship between those pipeline latency outputs. You have a latency 1, 2, 3, and 4 output per pipeline. And what is the relationship between those and the locations of memory on the belt? And then number 2 question was, do you have...
One at a time. I'll come back.
Sure.
Those latencies are purely registers. What actually happens as far as the belt is that the belt does not, as I say, it's not a shift register.
Sure.
There's a register here, and a register here, and a register here, and a register here. The value that's in that register is tagged with the frame ID of the operation that produced it and its belt number. There isn't actually no array. There's no register file. There's no SRAM, which is the belt. Instead, one of those consumers says, I want frame ID 742 belt number 3. And this register over here wakes up and says, oh, that's me here. The way we advance the belt is we tell all of those registers add 2 to your belt number. It's that easy.
So you have different crossbar, I guess, to track of the belts, the belt IDs. Is that right? So how do the
Sir, I'm sorry, I'm slightly deaf and I need that louder.
So you have a different crossbar which is managing the belt. Is that right? Different crossbars that is piping to different belt. So how does across the belt? How do they keep track of it? Which is belt, like from the one layer to the next layer, how they keep track of what is the belt numbers or individual numbers between different crossbars.
Dave, could you take a break and repeat the question for me?
So I guess you have different crossbars.
I'm sorry, it's my hearing. And it's not that I don't understand your questions, that I can't
I don't
hear
think
you.
I understand this question either because I know it too well. There's one crossbar.
Oh, just
I mean,
one
but
crossbar.
there's two. Yeah, there's the two.
It's-
You're talking about the latency one, the latency
The
two.
crossbars are daisy chained. The latency 1 operations, which are time critical, clock critical, only go through the latency 1 crossbar. Everybody else goes through both of them, one after the other.
But
Yes.
I get the idea. Your question is similar to mine, which is how is it? Are you determining how to set all the muxes in the crossbar in a central way, or is it like a CAM-like way, like you're describing, where you just all the registers wake up and?
As I said, the implementation in hardware terms varies, and it's up to the people implementing it. A CAM is a perfectly reasonable way to do it. I just described it as being a CAM. Give me a frame ID and a belt number, and the guy raises his hand. That's a CAM. And it can be implemented that way. A completely different way of implementing that is that there is a hardware recognition of who is where, and we just directly route things through a crossbar, and the decode and issue logic keeps track of where things will be. It can be implemented several different ways.
Do in the crossbar 2 inputs ever compete over the same sync, or is it all statically scheduled such that never congestion or multiple inputs want to acquire the same output can happen?
Each pipeline has 2 inputs, and the code says which belt position will be those inputs. So there cannot be any collision there. It's just like an adder on a conventional machine. Well, it takes 2 input registers, and you can use the same or different registers. You can use the same or different belt numbers for your inputs. For your outputs, as I showed you, with those values coming down and having to be moved out of the way from register to register. Yes, if we didn't move them, they would be overwritten. And obviously they can't be overwritten, and so they get moved. But exactly how they get moved depends on the implementation. I showed you one in which essentially they simply daisy chained into successive registers within the same pipeline until they finally reached the last latency of those and then got moved off to a buffer of some kind. That's one way of doing it. They may simply be moved directly to a buffer immediately. That's another way of doing it. I leave those questions up to the hardware guys. If you want to know how a particular one is done, I'm not the right guy to tell you.
For SRAM, do you have multi-ported SRAM buried in there for anything? Or is, for example, the buffer space that the spiller uses, is that all single ported?
Again, you're down at the bit level of the implementation. It is required that a single belt position be able to feed data to every possible consumer of a particular cycle. That is, every one of those functional units may all be pulling B3, 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 B3. Now, when we're 30 operations wide and 2 inputs each, that's like 60 inputs. So you're certainly not doing 60 ported SRAM. Instead, what winds up actually happening is it's a single ported, if it's coming directly from a register, or the spiller does have to have SRAM. But it will be single ported for each of the values that are in there. But then that winds up going into one of these crossbars, and it's got repeaters so that as it goes along the wires. That's all that's necessary.
Okay.
Yes?
What are some of the things that a compiler that's generating code for this machine has to optimize that is distinct from like your typical superscalar processor today?
Well, I'm a compiler writer. I've done nearly 12. And I've had bitter experience of people who design chips and say, well, the magic's in the compiler, and they push that off until the last. It sounds like somebody else knows what I'm talking about. Yes. Consequently, we decided we weren't going to do that. And so this machine is designed to be compiler easy. There is, in fact, almost no optimization. I mean, we do the same constant folding optimizations that everybody else does. And in fact, we're in the process of converting to the LLVM so that we can make use of their optimizer precisely for this reason. But once you get down into the stuff that knows it's a belt, the only really important thing that the compiler can do is to schedule producers so that they're adjacent to consumers. And this is a very, very common technique in signal processing compilers, and the way you do it is time reversal. You schedule, you have a data flow, and this value is produced and then used by him, and then his result is used by him, and then his result, you take the bottom guy, the return operation that's going to return, and you schedule him. And then whatever the latency is for that operation, you schedule whoever is going to produce that value, and then you schedule whoever is going to produce that value. So you schedule in time reverse order. We didn't invent this. This is going back 40 years in signal processing as a compiler technique, so as to optimize the data flow latency, which of course is critical in signal processing codes. But other than that, no, there's almost nothing. This, in general, for any given operation, there's only one way to do it, so we don't have these humongous case selections of, well, if and only this funny kind of state occurred, then this particular combination of operations is slightly better than that particular combination of operations. We don't do that. It's pretty much a dirt simple vanilla compiler.
So it's even simpler, you're thinking?
In that.
What's the status on availability of emulator and compiler for public?
We had, for the public? Well, that's another story. It's been running in SIM for several years. I'll be honest and say that it would be polite to call the tool chain and everything else alpha grade. Nonetheless, the portions which are critical to having done the design are there, including on the hardware side, the critical components that have been done. Big hunks of the hardware have never even been touched. We haven't even touched the floating point unit. We probably will buy a floating point unit. We don't need a floating point unit. So there's big hunks of the hardware that are not done. Most of the software is reasonably far along, but far from stable. Far available from other people to play with. We're a tiny bootstrap startup. We're doing our best to get out of that state, but that's where we are now. In order to let the public play with it, we would have to be able to support the public, and we haven't got the resources. On the other hand, people who know enough that they are effectively self-supporting and can do an NDA, we can probably do a deal. Anything you come up with, we want to be ours, but yeah, we can probably do something. In fact.
Yeah, so I think you mentioned briefly that you might have some short vector support in the architecture. I'm curious, does that mean that different items on the belt might be different widths?
Each item on the belt is an independent operand.
I see.
It can be a byte,
Right.
a double, a quad, a vector of halves.
Does that limit which instructions can consume which belt items?
This hasn't been filed yet, right?
Oh.
You're talking about stuff that hasn't.
Filed.
Oh, does that limit which instructions can consume which belt items?
Come again?
Does that limit which instructions can consume which belt items?
They're just operands.
I see.
Whereas many machines, in order to cut down that enormous number of sources, they have separate register banks for integer, floating, and vector. The only reason for doing that is a pain in the butt for a lot of things. Things like, the conversion of floating point to integer, where you've got to move things from register to register, is a pain. In the hardware and architecture too, we don't do that. We just the belt holds an operand. Any kind of operand the machine supports.
So, what do you do for variable latency operations, for example, data cache misses?
Again, please.
What do you do for variable latency operations such as data cache misses?
So, for example, if you have a data cache and you might miss or you might succeed in one cycle, but you don't know if it's going to miss or not until later, how do you handle the variable timing on that?
Well, as I said, this talk was not cover the memory hierarchy, and the reason for that is not filed yet. However, that will be the next block of patents going in, and I believe that our next talk, which will probably be early next month, will in fact cover all of that area of the machine, including the answer to that. What I can tell you is what the programming consequences, not how we do it, but the programming consequences. And the consequences are effectively, we hide the L1 and L2 pretty much completely. And we hide DRAM, or at least we hide DRAM as far as what an out-of-order machine could. We are in order, but we are able to do so.
Meaning that you'll stall.
Hmm?
Meaning that you will stall.
No, no. We succeed in hiding the latency of both levels of cache, and can hide the latency of DRAM in those cases in which an out-of-order machine could hide the latency of DRAM. Now, of course, there are many cases like that random access into a hash table where nobody can hide the latency and we can't either. Yes?
Are you close to being able to make public an instruction set manual for this architecture?
Unfortunately, the instruction set reveals, by implication, some of the things which haven't been filed yet. Soon, we are. Last September, I guess it was, we realized that we had to respond to the fact that the U.S. patent law was changing. We had been in stealth mode up until that point. With the change from first to invent to first to file, we were in a situation where, guys, we can't keep on being in stealth mode. We are going to have to file these, and now. Well, Let me tell you, I am so thoroughly sick of doing patents. We have over 50 of them, 50. And I am sick of it. But on top of doing that, then a presentation like this is not a fast thing to create. So we're slowly in the process of getting it through. We're trying to do one presentation of a new area of the machine a month. This is actually a repeat of one which was done in June at Usenix Vail, the Usenix conference in Vail, Colorado.
I don't know if you can cover it, but for memory loads, do they go from memory eventually into the load spill buffers to handle the synchronization of timing, or will that be in a future talk?
Load works exactly like any other operation. It winds up at the front of the belt.
But you don't know when they will come in.
Yes, you do.
Okay.
Next question.
So you talked about family processors with different build sizes, different number of functional units, and you're also talking about statically scheduling the compiler. Does this mean you need to create separate binaries for each different build size?
We use the same device that the IBM did for the System 38 and the AS400 and its descendants, which had a single uniform instruction set which ran on every machine and has been running on every machine for the last 40 years. And the way they do that is that the last step of installing a binary onto the machine is it winds up being specialized from a platform abstract independent representation to what actually is the bitsies on that machine. Consequently, the individual family members at the bit level are incompatible in terms of their instructions. But at the load module level, you can run any load module on any unit.
Nice.
So can you comment about performance? Basically, if you have 33 functional units working in parallel, what kind of effective instructions per count you get, and then what type of application code and so on?
Well, gold there is not intended to be an HPC chip. Its intended target market is essentially a server for the kinds of things that Google would have in its service. Consequently, it's got a lot of operations, a lot of slots, but the vector height is not very high. A high-performance chip intended for selling to NASA or somebody like that would have far more floating point units. Gold's only got 2 floating point units. The equivalent high performance will have 8 floating point units and be taking 128 bytes at a time. So the performance varies across from member to member. It depends entirely on which chip that you're talking about. Have I answered your question?
Well, but yes, I had a slightly different questions. At least I thought I was.
Let's try again.
So let's say if you take typical server workload, right? I don't know, spec CPU. What kind of IPC you would get on typical member of the family?
Well,
is it possible?
The only thing that we can do without actually running people's code is saying what is the peak. That gold can issue 33 operations per cycle, sustained.
But that is peak. That's not simulated performance.
It can do this. Now, I'll give you an example. A while back there was a contest, programming contest, for who would be able to get the best performance out of the Unix WC. which is the word count utility in units. And this was a contest with entrants, with people doing this in assembly language with really clever tricks. You're permitted to do absolutely anything in there. It turns out that the code in the contest, all you had to do was count the number of words and the number of characters came out of your I/O, but the number of words and the number of lines. Actual modern WC actually adds a third item to that, is it also has to keep track of what is the longest line. You can look at the man page to see what the rules are for WC. The naive code for WC is a get a character, enter a switch. If it's a blank, do this. If it's a line feed, do that, etc. What you do with that in a mill, at gold, for example, what you do with that in a mill is that you if convert, that first you turn the switch into a string of ifs. Standard compiler technique, getting rid of sparse switches. So you convert it into a string of ifs. Then you do if conversion of the ifs to turn those into a data flow, using what would be, for example, on if you were doing this for x86, it would turn into conditional moves. This gets rid of the branches so that you don't have any branches in there except the one going around the loop, because the branches mispredict something awful on WC. So that's your basic block of code. But after you've done that process, you've got one loop with all of this, which is essentially doing all the branches down that switch in parallel. WC on gold, that whole loop, one character, is 25 operations, one cycle. So we're processing one character per cycle out of the input, and doing it with 25 ops that are issued simultaneously. This is what pipelining can do for you. If you're talking non-pipeline code, then you've got to talk about the code. If, classic example, if you've got a data flow, well, I have to do this in order to do that, and then I have to do that in order to do that. We're going to do one at a time just like everybody else, because the program semantics call for it. All that width isn't going to buy you a thing. The width is intended for pipeline, because 80% of code is pipeline on us. Others?
Does this architecture have condition codes? Does it have condition codes?
Condition codes. No, it does not. The machine maintains no global state at all. No global application state like the condition codes are. The value, everything is represented as belt types. In back?
So in a register machine, it's pretty straightforward to inspect the stack, and certain parts of your language runtime often need to inspect the stack. Your profiler, your garbage collector, performance critical, your crash handler. And architectures which have sort of squirreled some of the activation state away in hardware like Spark, this can be a little more expensive than it would be on a straightforward register machine. So what is the implication on an architecture like yours when stack inspection is a critical operation?
Okay. You I can hear.
So,
can you repeat it?
So if you're going to do garbage collection,
right,
you have to scan total program state.
Yep.
A lot of architectures will spill all internal state to memory so that you can then scan it. Is that the sort of operation you'd have to do with all the belts?
Garbage collectors will always wind up special handling the registers in a conventional machine, because the registers are part of the base state. And similarly, on our machine, you would special handle the belt. More likely, however, what you would wind up doing is making use of the facilities that we have to support debugging. When you are when you're deep in a nested function and you want to enter the debugger, you frequently want to be able to inspect the state of a function which is not the top function. And that state is down inside the spiller, because that's what happens when you make the call, is that state that's winds up down in the spiller. There is hardware access and an API to support access from a debugger so that can be looked at. And a garbage collector would make use of that API.
What's the cost?
Just memory.
Just over.
Okay. The API would actually wind up flushing the spiller's internal SRAM, but that would have been happened anyway long before, just in the course of calling the debugger and then calling several other functions, that would have happened anyway lazily.
That's an operation on the Spark tends to make the Spark somewhat slower than other architectures when you're needing to invoke a garbage collector or profile.
You've got to go look at that. Once you're looking at that, the memory scan is, well, not the same as everybody else. We're running past 9. Folks want to call it, or would you like me to? I love to brag about the baby. I'm getting the signal over here to call it a night. Thank you for.
Do you know where the memory subsystem talk will be? Will that be in Stanford?
No, the next one at Stanford is in October, and then February are our Stanford dates. The next talk. Sign up for our mailing list.
Okay.
That will get you the correct information.